Welcome to this introduction to Brownian motion. In this video, we will explore the fascinating mathematical concept of Brownian motion, its properties and applications across different fields. Brownian motion was first observed by the botanist Robert Brown in 1827, when studying pollen particles suspended in water. He noticed that these particles exhibit random jittery movements. Almost 80 years after, Albert Einstein provided a theoretical explanation for this phenomenon in 1905, connecting it to the kinetic theory of heat. Later, mathematician Robert Wiener developed the rigorous mathematical foundation for Brownian motion, which is why it is sometimes called the Wiener process. Mathematically, Brownian motion is defined as a continuous time stochastic process. It starts at zero, has independent increments, and these increments follows a normal distribution with mean zero, variance equal to the time difference. One of its most fascinating property is that its sample paths are continuous everywhere, but it is non-differentiable almost everywhere, meaning it's incredibly jagged at every scale. Here we see two sample paths of one-dimensional Brownian motion. Notice how each path wanders up and down randomly in different ways. These are just two possible variations. Each time we simulate a Brownian motion, we get a different path. The unpredictability of this path is what makes Brownian motion so useful for modeling random phenomena. Brownian motion has several important mathematical properties. It satisfies the Markov property, meaning its future behavior depends only on its current state, not its past. It is also a martingale, which means its expected future value equals its current value. The scaling property shows how Brownian motion looks statistically the same when we rescale both time and space appropriately. These properties makes it a fundamental building block in stochastic calculus. Also, it satisfies the so-called refraction principle, and its quadratic variation up to time t is equal to t. Brownian motion can be extended to multiple dimensions by considering independent Brownian motions along each coordinate axis. Two-dimensional Brownian motion has the fascinating property that it will eventually visit every point in the plane, and it will do so infinitely often. However, in three or more dimensions, Brownian motion is transient. It almost surely never return to its starting point. This demonstrates how dimensionality of space dramatically affects random process.